we are going to develop one circuit which is going to be like this. Here we are going to have ammeter plus minus. Then here we are going to have a voltmeter, which is our plus minus here. So we have to connect one voltmeter to measure the voltage across this. So here all the elements are connected in parallel. So there will be some current division here and here. This will be I1 and you can consider as I2 and this as I1. So now we have to find I, and we have to see whether KCL is satisfied or not at this end, at this node. So I is equal to I1 plus I2. So here you know that I is the incoming current and I1 and I2 are the outgoing current. So we have to check whether the incoming current is equal to outgoing current or not. Okay, this is what we need to do. This is the circuit which we need to connect it here. Okay, so two parallel resistance with with a voltage source in parallel, and an ammeter is connected in series with this voltage source. Okay, so for connecting this circuit, what you have to do is you go to this terminal 1. You just go and click the left click and you just drag it. You'll be getting a wire and you just drop it on terminal number 3. If you drop it on terminal number 3, then there will be one wire will be connected between the terminal 1 and 3. Similarly, you come here, click this point, use left click and drag it and drop it on terminal number 10. So similarly, you have to connect this terminal number 11 to terminal number 4, then terminal number 4 to terminal number 5, and terminal number 6 to terminal number 9. So here there is one more terminal that is called as ground. That ground should be connected to the terminal number 9. That ground should be connected to the terminal number 9. So it is like you can see here that the ground is connected to this point. Okay, so then we just need to connect the voltmeter. The voltmeter need to be connected across the terminals terminal 10 and this 8 and 11. So we have connected here. Now what we need to do is we have to choose the DC voltage and we have to choose the resistance value. Then we have to find the current flowing through that particular circuit. Okay, so here you can change here, see here that there is an option named as control. In that control, 3 things are there. One is DC volt, resistance 1 and resistance 2. Okay, so here if you change this, this is the resistance 2 value and the current flowing through this is considered as I1 as per their labels. And similarly, this is resistance 1, the current flowing through that is R2. Resistance is R1 and the current flowing through that is okay. Now what you need to do, you just need to change the DC voltage, just need to change the resistance value and you have to find the readings. So before you give the data, you just give check connection option. If you just click it to the check connection option, it will be saying that right connection, set resistance and DC input voltage. So you just set the DC input voltage and the resistance value, you just check it and you just give add to table. So once you give add to table, the data will be moved to this table. You can see here that voltage and current. Okay, what you have to do is you have to note down the current value and the voltage value. So here I1 you measure, I2 you measure, and this is the voltage across the individual elements. So you measure these 3. Other than that, you measure this current. So 3 currents you need to measure and 1 voltage you need to measure. So this is for one particular set of reading. Then you change the DC voltage and you check the current flowing through that individual elements and you find I1, I2, and this is the overall current, that is I. Okay, so here as per this circuit, this is I1, this is I2, and this is R1, this is R2, and the current flowing through here that we are measuring, this is I. So what are all you have to plot? You have to plot V, not plot, you just note down the values of V, I, I1 and I2. Then you check whether these 3 are satisfied. Means I is equal to I1 plus I2. You just check whether I1 plus I2 is getting satisfied or not. That alone you have to check in the Kirchhoff's voltage law experiment. Here it is mentioned as Ohm's law, but we are going to perform KCL with this link. Okay. So now what you need to do, you just change the voltage, just change the voltage magnitude, and you check whether the current is different for different voltage source or not, and you check the sum of currents is equal to 0 or not. Means the incoming plus outgoing should be equal to 0 at any particular node. So you have to check this point whether the incoming plus outgoing is equal to 0, or you have to check whether the incoming current is equal to sum of outgoing current. Okay, you have to check this. So this is summation of outgoing current, this is summation of incoming current. So always your summation of incoming current should be equal to the summation of outgoing current, or the sum of incoming plus outgoing should be equal to 0. So that thing you need to verify in the Kirchhoff's voltage law, Kirchhoff's current law. So here you just need to change the voltage value, and you have to set the resistance value, and you have to take the links and verify whether the KCL is satisfied or not. Okay. In case if you want to remove the connection, suppose from here to here I have given one connection. Okay, but this is a wrong connection. If I want to remove it, I have to click this option 1. If I click the number 1, then the connection will be disabled. Okay, so you can see here that I am connecting between terminal 1 and 3. If I am connecting the terminal between 1 and 3, then if I want to remove this connection, then I have to click this particular number. Wherever I want to remove the connections, in that particular number I have to click it, and I have to remove the connection. Then I can connect wherever I want. Okay, for connecting, you have to go there, just click it on the left, use mouse, left click you use, then you just drag it and put it on the another terminal. To remove it, you just click on that number, it will be removing it automatically. Okay, so this is for KCL. Similarly, KVL also, it is having the simple circuit. Even though you would have done before, we will just do it in online, because our end semester examination will be in online mostly. Okay. So this is another simple circuit. Here we are having a voltage source, and we are having two resistors in series.
Sir.
Okay. So yes.
Sir. Sir, I also tried that parallel circuit, but in that I1 and I2 values are not showing.
See, you have to give add to table option, then only it will be coming.
Sir, I did that add to table option. In that they just fill the V and I total, not I1 and I2.
You click the resistance values somewhere, and you just click the DC voltage. Then you give check connection. Okay, I did not connect it. So I have given the connection now. The connection is correct now. I give add to table. You can see that after I give add to table, the values are displayed. In the control, you click on the DC voltage somewhere, resistance R1 somewhere, and R2 somewhere. Then after that, you give the add to table, then the current magnitude will change. Is it fine?
Fine. Yes, sir, yes.
Okay. So then for the KVL, we will be taking the simple circuit like this. In this, we are having resistance R1 here and R2 here. So now what we have to do, we have to measure the voltage across this. We are putting an voltmeter and we are measuring the voltage across this, plus minus. Then you are going to give some voltage across this. So this voltage will be equal to sum of these voltages. This voltmeter will give the voltage across both the resistors. Then based on the current flowing through this, you find V1 and V2, and you check whether V1 plus V2 is equal to V or not. What is this V? This V is the source voltage. So this is like, this is the voltage drop. These two are voltage drop, and this is voltage rise. So here summation of voltage drop is equal to summation of voltage rise. For the summation of voltage rise minus the summation of voltage rise plus summation of voltage drop is equal to 0. You can try any one of this, but you just show that the voltage drop, summation of voltage drop is equal to summation of voltage rise. That we need to see. So here in this circuit, we are having only one voltage rise because we are having only one source and we are going to give connection in this fashion. Okay. So here we are having an ammeter. Here you are having an ammeter, that is A. This is plus minus. Now what you need to do is just give the connection as per this diagram. So you just connect 1 and 3, then you connect 3 and 7, then you connect 8 and 11. Then this two terminals you connect, then 11 to this ammeter 1 end, the ammeter another should be connected to this terminal 6, and this ground should be connected to this terminal 6. Now we have completed the circuit. Now after we complete the circuit, what we have to do, we have to give some DC voltage magnitude and we have to give some resistance value. Some value we have to give. Then after you give, you can first check the connection. It is showing that right connection, set resistance and input DC voltage. Then after you check the connection, you can see that these options are enabled. If you see these options are enabled, give add to table, then it will be giving V1 and V2. So here you can see it very clearly that V1 and V2 are directly given or displayed. Then here the overall voltage is there. So obviously if you add V1 and V2, we will be getting the overall voltage as 10. So like this, you change the input voltage and you take the readings of V1 and V2. Similarly, you calculate V1 and V2 by yourself by multiplying the resistance and the current value and you compare it with the measured value. This is a measured value. For calculation, you use this current and this resistance value and check it on your own whether KVL is satisfied or not. Okay, so two things we are going to do. Previous one is KCL and here it is KVL. Both are very simple circuits. You just follow the procedures. You just give the connections and you just make the connection and find the values and verify it. Okay, so this
Sir,
is
how
for the
did you
KCL
get to
KVL.
this page, sir?
I will send you links.
Okay, sir. Okay,
So
okay.
there is one Word document. I will send you the Word document. Okay, as of now, I can send you in chat box as KVL. Okay, I have shared it. You can just go through it.
This we had, I think. This is KV. This is for KVL. This we had.
Okay. Okay, this is for KVL. Actually, for KCL, just a minute. Okay, that is for KCL. The previous link is for KCL, not for KVL. And for KVL, this is the link. Okay, link I will send you in PDF or Word document. You can go through it later. Okay. Then next is Thevenin's theorem and superposition theorem. We will start with superposition theorem. See, I will be completing 3 or 4 experiments today itself. Okay. Thevenin, superposition, RLC circuit, load test, and open circuit test. I will be completing it by today itself. Okay, because all will take not more than 5 to 10 minutes. So we'll be completing all the experiment. Then you can go through the recording. If you're having doubt, you can send me a message in MS Teams itself. Okay, so we will start with superposition theorem.
Sir, one more thing, sir.
Yes.
Now, as you shown us to like made the connection using the clicking and all. So should we, sir, take the screenshot and paste it in that assignment, or we should draw it?
Say it again.
Sir, we should
Say it
take the
again.
screenshots of the connections we made in the simulator, or we should draw it ourselves.
See, when you write the circuit diagram, I mean, when you draw the circuit diagram, you should draw it. But at the last, when you are including the results, there you have to take the snapshot of your circuit as well as your results.
Perfect, sir. And one more thing, sir. For the table, we should draw again, and then results we should share the screenshot also, or we just need that
Uh,
screenshot.
you should attach at the end of the write-up.
Sir, at the end in the result we will attach, but we should draw it ourselves
Yeah.
again.
No, no, not required.
Okay, sir. Thank you.
Results you don't need to draw it. You take the snapshot of it.
Um, and sir, where should we submit these assignments?
I will create assignments with the experiment name.
Okay, sir.
Okay. So next is superposition theorem. So here, this is the link for the superposition theorem. In this, they have given the detailed explanation about what they have done in this particular simulation they would have shown here. Okay, so now here there is an option named as a simulator. You just click that simulator option. Then below that simulator option, there is an option named as link to the simulator. You just click it. Then that simulation page will come. Okay, so here there is a circuit which is given here. Can anyone tell me what is the superposition theorem says? What superposition theorem says? Can anyone tell me?
Sir, when different vectors are in different phases, then adding them is we use superposition theorem.
No. Can anyone explain it in a very simple manner? Harsh Kumar. Harsh Kumar Sharma.
Hello, sir.
Yeah. Can you answer to the question? What the superposition theorem says? Kushagra Sharma. Kunal Yadav.
Yes, sir. Sir, it states that if in a circuit many power sources are connected, so through one element, if we need to find voltage, so we can find it like the algebraic sum of the voltages if they were to act independently, sir.
Okay, fine. Thank you. Thank you, Kunal. So consider a simple circuit. Let's say you are having a voltage source like this, and you are having a resistor like this, and you are having another resistor like this, and you are having another source here. So in superposition theorem, what we are going to do is, let's say you want to find the current flowing through the circuit, this particular loop, so this particular branch. Let's say this is I. You want to find the current I. So this I is partly it is coming from the source one, and another part is coming from source two. So what we are going to do in superposition theorem is we are going to consider only one source at a time, and we are going to see what is the contribution of this source for this current. Then similarly, in the second time, we are going to remove this source and we are going to consider another source, and we are going to see what is the contribution of this source on this current. So for example, for the first step, we have to keep the circuit like this, and we are having the voltage source. Let's say we are going to mention this as an I dash. Okay, we need I. Okay, we are considering only one source, that is source 1, and we have short circuited the source 2, and we have made this voltage as 0. Now we are finding I dash. Now this is for the circuit 1. For the second time, this is the step 1. This is step 1. And for step 2, we neglect the previous source which we had considered. Now we will include the another source. Now we are going to find the current flowing through this part, that is I double dash. Now, what is current? Overall current, that is I. When you are having both the sources, what is the current flowing through the resistor? That is I. That is given by sum of the current provided by the individual sources. I dash is the current provided by the and I double dash is the current which is provided by the second source. Now, what we are doing, when you are having a circuit like this, then we are considering only one source at a time, and we are finding the response of that source on that particular element. Either it may be a voltage or current. And similarly, we are considering for the second source, what is the response of the current for that particular source. We are finding it out. Then we are doing the algebraic sum in order to find the overall response. First, we are finding the individual response here, individual response here, and from that individual response, we are going to obtain the overall response when you are having both the sources together. Okay, so here it can be of voltage or it can be of current. Okay, V dash and V double dash. If I have asked you to find the voltage across this, so that is about that. But can anyone tell me why do you need to short circuit the voltage source? Why do you circuit the voltage source? And why do you need to open circuit the current source? Can anyone tell me? Because in superposition theorem, when you are considering only one source, the other source should be short circuited or open circuited. Depends on whether it is a voltage source or current source. If it is a voltage source, we will be short circuiting it. If it is a current source, we will be open circuiting it. Can anyone tell me why we have to follow this? This is in your syllabus, unit 1. Of course, this would have been completed very long back. So can anyone answer me why it is like that?
Sir, can you again repeat the question? I couldn't understand the questions.
See, here this is step 1. In step 1, I have short circuited the voltage source, right? If I had a current source, I would have open circuited that current source for this particular circuit. Can anyone tell me why did I short circuit this? That is my question.
Sir, you short circuited the current source, right?
No. You short circuit the voltage source. I short circuited the voltage source. I am asking why you short.
Because sir, because of the resistance, the voltage source has the infinite resistance.
Voltage source is having zero resistance.
Sorry, sir, sorry.
Okay. Can anyone answer me to this question?
Sir, we are only seeing the effect of any single voltage source. So, whatever we are calculating, I mean, effect of that voltage source should not come in this.
No. See, my point is very simple. I understand this source effective should not be there. Okay. Then in that case, my point is very simple. I have made a short circuit. Why I did not made open circuit for voltage source? That is my question. Whether my question is clear? In superposition or Thevenin or Norton theorem, whenever in superposition, whenever you want to consider one source, other source should be eliminated. If it is a current source, you will be open circuiting it, and if it is a voltage source, you will be short circuiting it. My question is why you are doing open circuit for current source and why you are doing short circuit for voltage source? And that is my first question. Similarly, in finding Thevenin and Norton theorem, in Thevenin and Norton theorem, when you are finding R Thevenin or Z Thevenin, similarly R Norton or Z Norton, what you will be doing, you will be open circuiting the current source and short circuiting the
Open circuiting
the current source and circuiting the voltage source. I am asking.
Sir,
Bharat,
we
don't get
open
confused.
circuit the current source because we are eliminating all the current sources. We should because we don't want the current to go through that way, sir. That's why we open circuit that. No current will be go through that wire.
That I agree. But on what basis you chose that value as infinite? It is an infinite value, right?
Because sir,
Your
there is
open circuiting
no...
means it is an.
Yes, sir. You continue, sir, please.
No, my question is, you are making an infinite resistance. This is an infinite resistance.
Yes,
So
sir.
why you are considering infinite resistance here?
So that no current passes through it, sir.
No. That is, the resistance is infinite.
Yes,
That's
sir.
why there is no current passing through it.
Correct, sir.
You are saying in the reverse way. Actually, this is the first, then this is second. Means you are making the resistance as infinite. That's why it is becoming open circuit. I am asking why it is like that. Why you are making resistance as infinite? On what basis this resistance as infinite came into the picture? Okay, I
Again, sir,
think you
because we
people
don't
did not
want any
answer.
current to pass through that.
See, okay, I will try and change the question in this way. See, actually, what we are doing, we are just replacing the voltage source and current source with its equivalent internal resistance. That is what we are doing. Okay, I'll put the statement again. We are replacing the voltage source or current source with its internal resistance of ideal independent sources. If it is an ideal independent voltage source, its internal resistance is 0. If it is an current source, its internal resistance is infinite. So my question is, why internal resistance is 0 for ideal independent voltage source? Why internal resistance is infinite for the ideal independent current source? So because of this internal resistance only, we are keeping this here. Okay, so okay, fine. Leave it. You just think about it. So now voltage source should be short circuited and current source should be open circuited. Okay, we are having this circuit. Now what we are going to do? We are going to apply superposition theorem. This is our circuit. This is our circuit. And we are going to find the overall response of this circuit in this current. Mean we are going to find the overall current which is flowing through this branch, that is I, and we are going to have the circuit in two steps. That is this step. This is the first step, and this is the step one, and we are going to find that is I dash, and we are going to find the current I double dash by considering the source like this. Okay, so now I is equal to I dash plus I double dash. Okay, so this three circuits we are going to not we are going to make, the circuit is already there. We have to select it accordingly, and we are going to perform this experiment. So this will be the first case. This will be the first case. First we will be finding the overall current. In the second case we will be finding the I dash, which is the current which is supplied by this voltage source, and we are going to find I double dash. That is the third step. With this, we are going to find the current supplied by this voltage source, that is I double dash. Then we are going to check whether I is equal to I dash plus I double dash or not. Okay. So summation of I dash plus I double dash. So the overall response will be equal to the sum of the integer responses. That is what the superposition theorem says. Okay. So if you, when you are having multiple sources in your circuit, the overall response when you are considering all the sources will be equal to the sum of the responses when individual sources are connected. Those summation, that is algebraic summation of those responses when individual sources are connected, will be equal to the overall response of the system when you have all the sources connected together. Okay, so that we are going to do the simulation in this thing. So same circuit, here there are two options, power, short. Okay, so in this first circuit, here we are having one voltage source and here we are having another voltage source, right? So when you are having two voltage sources like this, here we have to choose the option power. Here you can see that power option is selected and here power option is selected. Already some voltage magnitudes are given. Some this is the voltage magnitude, and this is also another voltage magnitude. This is the source on voltage magnitude and this is source to voltage magnitude. Now we have to select both should be in power. Then once you select both should be in the power in the drop down, this will be coming as a circuit one. So this is considered as case one in this simulation thing. So after you connect it in power in both the things, you can give the option as simulate. If you give the option as simulate, you can see here that here it is like this. If you give power, this is like this source is connected to this resistor, and this source is connected to the resistor, this resistor. So the circuit is flown like this. So this you can see here that this is the switch. This switch is closed when you have given the option as power. Okay. So if you choose it as a short, you can see here that I'm just okay. This will not work here. So you just give power option for both, and you give the simulate. If you give the simulate, it will show the current 1, current 2, and current 3. Means the current flowing through this, that is I1, you can consider. Then current flowing through this is I2. Then the current flowing through this is I. So I is equal to I1 plus I2. This is for when both the sources are connected in the circuit. Okay, this is for case 1. And for case 2, what we have to do is you have to short circuit the second source, and you have to find the current in the individual element, and now you have to find the current flowing through this branch. Now what you have to do, so the voltage value are similar like the previous case, nothing is changed. Now what I am doing, I am short circuiting the second source. So I have given the short circuit. So you can see here that the switch is closed here now. The circuit will be closed like this. So now there is a switch. If I give power, okay, so actually if I had given power, this will be connected like this. There is a switch here. That switch is closed now. If I give it as a short, then these two terminals will be connected. This switch will be open, and these two will be closed. There will be a connection between this dot and this terminal B. Okay. So now for this, we have to connect this as power and this one as short. Then you just give the option as simulate. Then all the readings will be shown. You just note it down. In the case 1, you should note down I1, I2, I3, I2 and this current. In case 2, you have to find the current which is flowing here. That is some current. You can consider it as I dash. So this circuit you can consider it as I dash. That is what we are doing now. This is for case 2, and for case 3, you have to do in the another way. Means you have to short circuit the first source, and you have to give the supply with the second source. So I have changed this option as power, and I have changed this option as short. So since I have given the option as short, this switch will be open now, and this will be connected between this dot and this terminal B. Similarly, there will be a connection between this dot and this terminal B. So if I give simulate, you can see that now the switch is moved here. Then the circuit is closed through this path. So now here with this I'm supplying. This is the 110 volt source. So with this I'm supplying. With this I'm going to find the current which is flowing through this path. That is I double dash. So this case is for this one. So here I have the source, and it is giving the current I double dash. Now I have to add I dash plus I double dash. This is with the case 2, and this is with the case 3. So now what I have to do, in case 1 I got some current. In case 1 I got some current that is flowing through this particular branch. Flowing through this particular branch, I found some current. Now I have to compare this current I with the summation of I dash and I double dash. Okay, so this is very easy. You don't need to do much work. So what you do, you can choose for the case 1, you choose one voltage. For you choose different voltages for different sources. Then you choose different resistance accordingly. You choose any resistance accordingly and check the circuit. Okay, but if you are changing the voltage value and resistance value for this circuit, this is for case 1. Then similarly for case 2 and case 3, you should use the same voltage and resistance value only. Unless and until you have the same voltage and resistance value of the system, you cannot verify the superposition theorem, because once even a single resistance changes, the complete response will change. So because of that, you choose the same voltage and resistance value for all the circuits given. Okay, is it fine? Do you have any doubt in this? So if you don't know which step what you have to do, clearly the instruction is given here. With this instruction, you just follow this instruction. then you give the simulate option, then there is an ammeter reading which is given here. You just note down this value. So similarly, you find the readings for 4 set of values and you just fill the table. Okay, you choose 4 set of values and you fill the table for 4 readings. So you have to verify the superposition theorem for 4 different set of readings. Is that clear? If you have any doubt, you can let me know. Else, shall I proceed further?
Proceed, sir.
So the next one is Thevenin theorem. So why we are doing Thevenin theorem? Can anyone tell me why you are doing Thevenin's theorem? What is the requirement of Thevenin's theorem?
Sir, to get the total resistance or total voltage of circuit?
No. Kriti Agarwal. Kriti Agarwal. Krishna Soni.
Yes, sir.
Can you answer to the question?
Sir,
Do you know what
because
question I asked?
sir, please repeat.
Do you know what question I asked?
Sir, please repeat.
No, what you are doing? You are talking, right? You are talking with someone. I were able to see it that you are talking with someone.
Sorry, sir.
Were you talking with someone?
No, sir, I am not talking with anyone else.
Okay, Kriti Gupta. Kriti Agarwal. Kriti Gupta. Konaru. Konaru Yuvakishore. Sai Teja. Sai Teja. Kalyan Kumar. Jaya Singh.
Yes, sir.
Jaya Singh, can you tell me what was the question I asked?
So what is Thevenin's theorem? So
Can you
why do
answer to
we?
the question?
So because we can simplify the circuit through Thevenin's theorem, and we can replace with Thevenin's resistance and Thevenin's voltage, so that easily we can find out the current and all different things in the circuit. It's a way to simplify the circuit.
Okay, thank you, Jaya Singh. Jay Agarwal. Jay Agarwal. Jatin Grover.
Yes, sir.
Indra Raj. Yeah, Jatin Grover.
Yes,
One girl answered the answer to the question now. Can you
Yes, sir.
tell me whether it is right or wrong?
yes, sir, it is
Sir,
right.
Thevenin theorem is, she is right, sir. So basically, we simplify the circuit into a Thevenin resistance and a voltage so that we can find out the value easier. We can replace it by the two values like Thevenin resistance and the voltage. So as we simplify the linear circuit.
Okay. Indra Raj, can you tell me what are the minimum requirement if you want to replace some circuit with its Thevenin equivalent?
So basically, we replace the whole circuit by a source and a resistance,
No.
equivalent resistance.
No, my question is what is the minimum requirements? What are the basic things need to be there if you want to convert a circuit from a normal circuit to a Thevenin equivalent?
So there should be a
There are 4
resistance and a
basic
source.
conditions. No, not that. There is a 4 basic conditions. Only if the circuit meet those conditions, then only you can convert from a normal circuit to the Thevenin equivalent. Do you know that?
One condition I think, sir. Sir, the source should be linear conditions should be followed, sir, in circuit bilateral.
Okay. Okay, fine. Harsh Asnani. Harsh Asnani. Gitla Shruti. Gitla Shruti. Sai Rupa. Sai Rupa. Falak Khan. Divyanshu Agarwal.
Yes, sir.
Divyansh Gangwar. Yeah, Divyanshu Agarwal. Can you tell me what are the 4 essential conditions if you want to convert some circuit from a simple circuit to a Thevenin equivalent?
Sir, the circuit must be linear, active, and bilateral. These 3 are
Active.
there. Yes, sir.
Only 3. Anything else?
And sir, condition I don't
What do you
remember,
mean by
but I
bilateral?
think
Okay, what do you mean by bilateral?
bilateral means like if, for example, there is a resistor, then if you pass current in any of the direction, then it behaves in the same way. So it's like if diode is there, then if you pass the current in different directions, then it behaves differently. So bilateral means it behaves in the same way for any direction of current.
Okay, fine. Thank you. Divyansh Gangwar. Dhanraj.
Yes, sir.
Pankaj Gautam. Yeah, Dhanraj, you are awake. Good. So one of your friends told about 3 conditions. Can you tell me the 4th condition? At least can you tell me what are the 3 conditions first?
So the first condition was the circuit should be linear, and second
So
was
what do you mean
the
by
circuit
linear?
contain. So linear should like it should follow Ohm's law, all components and all. And the second condition was it should contain active sources, not any independent sources and all. And the third condition was bilateral, like components should be bilateral. Uh, I don't know fourth one.
Okay, fine. Thank you. Devan Srivatsava.
Yes, sir.
Yeah. Can you tell me why do you need to go for Thevenin's theorem?
Sir, to simplify the circuit, and we can simplify the circuit using Thevenin's theorem to Thevenin's voltage
Why you
and
need to
Thevenin's.
simplify?
Sorry, sir.
You need to simplify the circuit.
Sir, to calculate values like current through any load easily, as in simplified circuit we can calculate it very easily. So that's why we simplify.
Okay, fine. Okay, fine. See, consider that you are having a circuit like this. You are having some circuit like this. Okay. So now, and you are going to connect the load here. You are going to connect the load here. So it can be a resistor or whatever the load you want to connect. You can connect here. Let's say these are terminals A and B. So now you can consider this whole circuit. This is the main thing for a Thevenin theorem. So this circuit is a fixed one. This complete circuit is not going to change. This complete circuit is not going to change. Only your load is going to change. Okay, so if the complete circuit is fixed and only your load is changed, then if you want to find the load current alone, let's say you want to find the load current. So if you don't have Thevenin theorem, obviously you can apply mesh analysis or nodal analysis, or even you can use circuit reduction in order to find the current flowing through this particular load. The problem here is the most of the circuit is fixed. Most of the circuit is fixed or remains constant, whereas only your load is changing. Okay, this is the main condition for Thevenin theorem. So when such a condition occurs, you want to know what is the current flowing through the resistor, this particular load resistor. Then what is the voltage across this load? If you want to find the voltage across the load and the current through the load, if you are using mesh analysis or nodal analysis or circuit reduction, every time whenever you want to find the current or voltage, you have to repeatedly write the equations. So for this particular circuit, you are having node, this is the node 1, and you are having this as node 2. So if you are implementing nodal analysis, you need two equations to write. If you're using mesh analysis, this is the first equation, second equation, third equation you will be writing, and this is the fourth equation you will be writing. So for mesh analysis, you need minimum 4 equations to solve this particular circuit. Now, when the load alone is changing, if you're using mesh analysis or nodal analysis, every time you have to solve all the equations and you have to find the voltage across the resistor or voltage across the load or the current through the load. So the point is, only the load resistance is changing. Only if the load resistance or load is changing, why do we need to solve the circuit again repeatedly in order to find the current flowing through the load? Because this circuit is fixed. When this circuit is fixed, why do we need to solve this circuit repeatedly in order to find the current flowing through this load? Only when the load resistance or load impedance is changing. So for this only, Thevenin came to an idea to reduce this complete circuit into a voltage source with a resistor in series. For a voltage source with a resistor in series, this complete fixed circuit, we are replacing it with a voltage source with a resistor in series. So this voltage source, we are going to say it as a Thevenin voltage, and this resistance, we are going to tell it as a Thevenin resistance. Okay, so now what is the advantage for us? Now this complete Thevenin equivalent we have obtained like this. Okay, we have obtained like this. Now this is the load terminal. Now this is VTH, this is RTH. Now if we are asked to find the current flowing through this part, you can directly substitute in this equation VTH divided by RTH plus R. On the trivial equation around this slope. If you are writing that equation, we will be getting the one equation. Then you can rearrange that equation in order to find the current. Now the point is, if the load resistance here is a variable 1, you can just put the RL value here and you can just find the current flowing through the circuit at a very easy manner. Okay, is it clear? We are going to fix the fixed circuit with the Thevenin resistance and voltage in series, and just we are going to put the load across the terminal. This is the A and B terminal. Before that, whatever the circuit were there, that we have put it as VTH and RTH. Okay, so for this, mainly 4 conditions it should be satisfied. The first one is it should be a linear. Then it is a bilateral, time invariant, and passive. So these things should be satisfied in order to reduce this circuit to this.
Sir, what is the
Okay,
fourth
so
one?
now actually the elements except the source, the elements which we are using, that should be a passive elements. Passive elements.
Oh, passive.
Except the source.
Okay, sir.
Okay. Okay, it is passive. So these 4 conditions should be there. Even though we are not directly saying like this, but these conditions are essential. They should be time invariant, not time variant. They should be time invariant. This is from the circuit elements point of view. When you are seeing from the circuit elements, that is whatever the resistor, inductor, capacitor, which that components you are using, except the sources, those elements should be linear, bilateral, time invariant, and passive components. Okay, your element should be like that. Then those should be replaced with a voltage source with a resistor in series. Now, another thing is time invariant. That is one thing. You keep in mind that only the load resistance can change. Rest of the circuit element parameter will never change. If it is 2 ohm, it is 2 ohm for always. If this is 10 volt, this is 10 volt for always. These values are not going to change. That is the basic thing which you need to understand. If the load resistor, if there is a resistor here, if that resistance is also changing, then this complete circuit is not fixed. If the complete circuit is not fixed, you cannot make this as a single Thevenin equivalent circuit like this. Okay, so I hope that you would have studied this in your subject. So let me not go much into that. So now we will come to this circuit. So in this circuit, what we are having is we are having a voltage source here. Then this is the circuit which is given here. So the load resistance is connected here. This is A and this is B. Okay. So now you are connecting a voltage source, that is V1. This is V1 that is connected here. And this is R1. This is R3. Now this is R2. Now, what should be your first step and second step? In Thevenin theorem, you have to find VTH. That should be your first step. And second step is R Thevenin. And the third step is finding the equivalent circuit. Now, in this particular circuit, when we are performing the simulation, initially what do we have to do is we have to choose power option here for this source, and we have to give power option for this load also. Okay, now if we give power option for this, the circuit will be connected like this. Okay, so if you give power option, then the load AB resistor, the resistor across the terminals A and B, you can consider this terminal as A and this terminal as B. So those two terminals will be connected, like this will be, circuit will be passing through this, current will be passing through this. So when you are giving power, these terminals will be connected, means it will be passing through the load terminal. Now when you are giving power, here they have already clearly mentioned circuit analysis to determine the load current. We want to find the load current. This is the load which is connected here. Then to get the load current, select switches S1 to power and S2 to load. Here, okay, here load is there. So load option is there. You can connect it to the load. So power option means here there is one more voltage source is here. You don't need to use that option. So you use the load option. If you give the load option, then load will be connected. If you choose the power option, there is a source at this point, that source will be connected. Okay, so since you give load, so the load will be connected like this. Now you give the simulate option. For already some values are given. So the current has come as 0.10645. Okay, so this is the first step. In the first step, what we are doing, we are having this circuit. In this circuit, we are going to include the load. After we include the load, you are just going to give the option of simulate. Then the current will be flowing through this path. Okay, so that is given by IL. That is set as 0.10645. Okay, so this is our first step. In the first step, we are finding the load current. In the second step, what we are doing, we are finding RTH. So here that is considered as case 2A. Okay, this is considered as case 2A. Okay, so in second step, actually what you need to do, you need to find V Thevenin. For finding V Thevenin, what do you need to do? You have to apply the source here, and you should be having a resistor here like this. Then you have to open circuit the load. You have to open circuit the load terminal. Then we have to switch on the circuit and we have to see what is the voltage across these terminals A and B. So this is case 2A. This is case 1. Okay. Case 2A is for finding the voltage, that is VTH, across this terminal. So what we have to do, we have to open circuit the load terminal and we are having a source. So here it is 110 volt. and here it is 100 ohm, and this is 300 ohm. So now with this circuit, we have to find the VTH across this terminal. So now you just give this connection as load. Sorry, no, so for this we have connected as intermediate. Intermediate mean we are open circuiting it. Okay, actually here there are three options like this. Okay, so there is a switch which you can connect it here or here or here. Okay, so similarly there is a switch like this on the bottom part. So this is power, this is intermediate, this is load. Okay, so in case one we want to connect up the load, so you will keep the switch to the load connection, the circuit will be closed like this. Okay, the circuit will be closed like this. Okay, then if you give intermediate, these two paths will be connected. If you give power, these two paths will be connected. So if you give power, this is a source. If you connect it as an intermediate, it is like open circuit. If you connect it as intermediate, it is an open circuit, means these two terminals will become open. Okay, and the third step is for third one is for the load, to connect the load across it. So now for case 2a, we have to choose power for this source which is available here, that is V1, and for here we have to choose it as a load. Then you give the simulate option. Sorry, this is case 2a. For case 2a, you have to give intermediate. So intermediate, you have to open circuit the terminals A and B. So for that we have to give intermediate. Then you give the option as simulate. So if you give the simulate option, you will be finding the voltage across this. This is nothing but 82.5. This is very easy because this is 110 volt. Now the current will be flowing only through this path. The current flowing through this path will be equal to 0 because it is open circuited. Now I can be written as 110 divided by 100 plus 300. So if you calculate this, okay, this 82.5 is Thevenin voltage. So if you find the current, you will be getting some current. So that current you multiply with 300 ohm, you will be getting some voltage. So that voltage now it is coming as 82.5. So now since there is no current passing through this path, there is no voltage drop across this resistor. So whatever the voltage across this 300 ohm resistor will be appearing across the terminals A and B. So here the voltage will be 82.5 and the VTH will also be 82.5. Okay, so this is for case 2a. For case 2b, what you need to do for case 2b, what you need to do, you have to open the load terminal, that is A and B, and you have to short circuit the voltage source and open circuit the current source. So I am short circuiting the voltage source and you are having a 300 ohm resistor here, and you have to find the R Thevenin from this end. So these two resistors are in parallel, and here you need to find these two resistors are in parallel. When you find the equivalent resistance, you will be getting a resistance like this. Then that resistance will be in series with this resistance. So here, for finding the Thevenin resistance, generally while you are calculating, you will be doing this calculation by circuit reduction. Here, the simulation you cannot do the circuit reduction. Further, what they are doing, they are applying a voltage source here, and they are, after they apply the voltage source here, they are finding the RTH across this terminals. Okay, so they are using a different procedure in order to find RTH. How they are finding RTHs? So here these two resistors are in parallel and this resistor are in series. Now we will consider one thing. So we'll consider this as 6 ohm and this as 6 ohm and this as 2 ohm, and let's say this as a 10 volt source. Now you don't know what is the overall resistance of this circuit. You don't know the overall resistance of this circuit. The simulator cannot find the overall resistance by itself. So what it is doing, instead of open circuiting it and do the circuit reduction, it is connecting a voltage source across the terminals A and B. After it connects the source across the terminals A and B, there will be some current which will be flowing out of this voltage source. Now, if you calculate that current, so that current will be 5. That current will be 5 ampere. Sorry, 2 ampere. Okay, because these two are in parallel, so you will be getting 3, then 3 plus 2. This is in series, then you will be getting 5 ohm. So I is equal to 10 divided by 5, you will be getting 2 ampere. Now, in this simulated, what they are doing, they are connecting this voltage source and they are finding the current flowing through that path. So instead of calculating this resistance by using the circuit reduction, they are taking the ratio of V divided by I. This V is the voltage magnitude of this source and this I is the current coming out of the voltage source. So this is 10 volt divided by the current which is coming out, that will be 2 ohm. Then the overall distance is 5. This is 2 ampere. Then the overall distance is 5 ohm. So if you calculate manually, what do you do generally? You will reduce the circuit reduction and you will find it out the equivalent resistance. That resistance is Thevenin resistance. But the simulator cannot do the circuit reduction in that manner. So what they are doing, they are connecting the voltage source. After they connect the voltage source, they are giving some magnitude for the voltage source. Then because of the magnitude of the voltage source, there is going to be some current flowing through that circuit. So then after the current flowing through the circuit, they are taking the ratio of the voltage source and the current coming out of the voltage source. Then if you are taking it, you will be getting the R Thevenin just by finding the ratio of voltage and current rather than doing circuit reduction. Okay, this obviously you might be knowing this, because if the circuit elements are having dependent voltage source or current source, then obviously you should use a voltage source or current source across the load terminals. You would have seen that, right? In your subject, you could have solved some problems which are based on dependent voltage source and current source, right?
Yes, sir.
Okay, then fine. So in that case, these things you will be knowing it. So just you are going to take the ratio of V and I in order to find the R Thevenin. So for case 2b, what do you need to do? For case 2b, you need to find the R Thevenin. So for finding the R Thevenin, you have to short circuit the source, because it is a voltage source. Since it is a voltage source, the left hand side thing is the voltage source that you are going to short circuit it. Then here we have to consider it as a power on the right hand side. Now if you consider power, we will be getting the circuit in this fashion. Now what we are going to do with this connection, we are going to find the RTH. So you just give the simulate, you can see here that we are getting RTH as 275 ohm. So here this is the voltage source 220 volt and the current 0.8 ampere. So this voltage source is the magnitude of the source which is connected here, and the current is the current coming out of that voltage source, that is 0.8 ohm. Then the Thevenin resistance is 275 ohm. Okay, so this is for finding the Thevenin resistance. 2a is for finding the Thevenin voltage and 2b is for finding the Thevenin resistance, and case 3 is for finding the load current. Now here it will be automatically taking this V Thevenin and R Thevenin which you had obtained in the previous circuits. Then here the load resistance is 500 ohm, because for this circuit we have considered as 500 ohm. Then if you give simulate, it will be giving the load current as 0.45. So now if you compare the case 3 result with the case 1 result, then both the current should be same. So that is what you are doing now. So what you have to do, so you change different voltage source and different resistance value and find the equivalent Thevenin resistance and find the load current. So like that you change it for two different set of readings. Then you have to verify with case 1 and case 3. You have to perform the calculations for all the experiments. You just don't copy the data from the simulation. You have to do the calculations also. Remember, you have to do the calculations also. Okay. So case 1 is for finding the load current directly. Case 2a is for finding the Thevenin voltage. Case 2b is for finding the Thevenin resistance. And case 3 is for finding the current which is based on the Thevenin equivalent circuit. Is it fine?
Okay, sir.
Do you have any doubt? Yeah, if you have any doubt, you can ask. If you have any doubt, you can ask. Else we can move to the next experiment. Okay, fine. So let me go to the next experiment, that is Rlc circuit. So in Rlc circuit, Here, this experiment, we don't need to give any connection again. You just go to the simulator. So here, it is very simple experiment. So in this, by default, you'll be getting some voltage and you'll be getting some resistance and inductance and capacitance. Now, what you do, initially, you can change the value of the inductance and you can change the value of the capacitance. Also, you can change the value of the resistance. So this is a series RLC circuit. So the circuit which you have here is series RLC, which is going to be somewhat like this. Okay, now what we are going to do, this is a variable, this is a variable, and this is a variable. So there is going to be a voltage source. So here we are using an auto transformer. So auto transformer we are having. Then we are going to take the output. So this is our initial condition. So now what you have to do, there is a ammeter here and there is a voltmeter here. And there is a voltmeter across individual elements, that is R, L, and C. There is a voltmeter across individual circuit element. So what you have to do here is, you have to draw the phasor diagram. So phasor diagram you have to draw between the resultant voltage and the resultant current. Okay. So if I take I as a reference, because I'm taking I as a reference because same current is flowing through all the elements. So I am taking I as a reference. Then if the complete circuit is behaving it as a resistive circuit, then the voltage, the resultant voltage will be in phase with the current. Whereas if it is an inductive circuit, you are changing the value of resistance, inductance, and capacitance. So if it is an inductive circuit, you know that the voltage should be leading the current, and this should be for the inductive circuit, and then the voltage should be lagging the current if it is a capacitive circuit. Right. If the capacitive effect is more, then voltage will be lagging the current. If the inductive effect is more, then the voltage will be leading the current. Then if the complete circuit is at the resonant condition, then the voltage across the resistor will be, the voltage across the resultant voltage will be in phase with the current. So these three conditions we are going to check. Okay. So first is in phase. The second one is the inductive.
Sir, for inductive, the voltage of inductor should be greater than capacitor, right?
Yeah, true. True.
Okay, sir. Now please continue.
Yeah. So in this, actually, if you plot the current with respect to the individual element for a resistor, the voltage across the resistor will be in phase with the current. The current is considered as reference because the same current is flowing through the element. If you see the inductor, the current will be here and the voltage will be leading 90 degree. This is for the pure inductor. And if it is a pure capacitor, you are having the current here and the voltage will be lagging the current by 90 degree. So this is VC, this is VL. Voltage across inductor, this is voltage across the capacitor, this is 90 degree. Now, when you are having all the three elements, now you can club all these phasor diagram. This is a phasor diagram. So here you can club everything. So you can club, this is I, and you can consider this as V, L, and you can consider this as V, C. Okay. So now the point is, if it is more inductive, then VL minus VC will be greater. I mean, it will be a positive value. Means here VL will be greater than VC if the circuit is behaving like more inductive. So since VL and VC are exactly opposite to each other, it should be having a resultant magnitude. So that resultant magnitude will be coming in the top because your VL minus VC is positive. This is for the case the circuit is behaving as an inductive circuit. When the circuit is behaving as a capacitive circuit, then that means that the VC is greater than VL. Because of that, the difference in voltage will be, if you take VC minus VL, that will be coming in this way, or this is fine. You can consider like this. So VC is greater than VL, then the overall magnitude between this voltage and inductive voltage and capacitive voltage, it will be coming in the downward. So if it is an inductive circuit, you are having VL minus VC here, then there should be a resultant voltage. Your voltage across the resistor can be somewhat here. This is the voltage across the resistor. This is the voltage across the inductor plus capacitor. The overall voltage between this inductor and capacitor is given here. So this is considered as VL minus VC. There should be a resultant voltage. You can do vector addition. You just project the horizontal component and vertical component, and you just do the intersection point. Then you connect these two. Okay, you connect the intersection point with this. Then you will be getting the resultant voltage. This is your resultant voltage. If the circuit is behaving like an inductive circuit, then your VR leads resultant voltage. RES, I'll put RES. The resultant voltage leads the current flowing through the circuit. Okay, so if it is a capacitive circuit, obviously it should be coming in the opposite direction. So your VR will be here, and this will be your VC. So this will be your VC minus VL. So your overall voltage will be coming here. Then it will be projected like this. The resultant you take here. Then this is the resultant voltage, V resultant. Okay, so here you can see here that the I leads resultant voltage by an angle, some angle. This is for capacitive circuit. For an inductive circuit, V leads I. Okay, so if it is a resistive circuit, or it is behaving like a resistive circuit, then resultant voltage will be in phase with the current. These are the three cases which we are going to check in the RLC analysis, nothing else. Okay, so you can consider this circuit. In this circuit, the initial voltage it is given as 110 volt. So what you do, you just change it to 220 volt, or you can also consider it as 110 volt. It's up to you. Now the maximum resistance of this resistor, rheostat should be 50 ohm. So you fix it like that. Now you keep the inductance value as 0 and the capacitance value as 0. If you do like that, these two is becoming like a short circuit. So now once you turn on the switch, then the circuit will be closed. You just give the closing option here. Okay, so now you can see here that the current is flowing through the circuit. This is a pure resistive circuit because I have given the capacitance and inductance value as 0. So because of that, there is no effect of resistor and inductor. You can see here that it is looking like a short circuit, right? So because of that, there is some current which is flowing through that circuit. So here there is a current which is given here. Then the voltage across the resistor is 220 volt, and voltage across the inductor is 0, and voltage across the capacitor is also 0. You note down these values, then you give fill the table option. Then you can note down the values. Power is also given, but power you are not going to do anything with the power here. Okay. Then the next is what you do. You change this inductance value to 30 millihenry. See, there are only three options. You can just drag it and put it. Initially it is 0, then you can put it at 30, then you can put it at 60 millihenry, and you can put it at 90 millihenry. So what you do, you first put at the 0 condition, then you just keep it at 30 millihenry. After you keep it at 30 millihenry, you can see here that there is some current, there is some voltage. In the earlier case, when it was a pure resistive circuit, the complete voltage was appearing across the resistor. Now some voltage is appearing across the inductor and some voltage is appearing across the capacitor, right? So because of that, now what is happening is some voltages are divided here. Okay, so now this circuit is behaving like an inductive circuit. So you can see here that you are getting positive value. If it is a positive value, then the circuit is inductive. If it is a negative value, the circuit is behaving like a, you can see here this value. I think it is visible to you. So there is a meter which is showing inductive and capacitive. So here it shows that whether the overall circuit is a inductive or capacitive part. Okay. So the voltage across this is 37.81. Here the voltage is 200 volt, and here the voltage across the capacitor is 0. So this is for the inductive circuit because we are having only the value for the inductor and we are having 0 value for the capacitor. Now you increase this capacitance value. Now you can see that the circuit is becoming from inductive to capacitive. That's why the angle has become negative. Okay, so actually you can we'll put the value 0 here, then just give the value as I have just filled the table. Then what I'm doing, I'm changing the capacitance value. You can see that after I included the capacitance value, now the capacitance effect is more. Because of that capacitance effect, you can see that the overall angle is becoming 33.735. This is the resultant angle, that is between the resultant voltage and the current. Okay, so now the circuit is behaving like a capacitive, that's why the angle is negative. Then you can increase the value and check what is the effect of the further increase in capacitance value. Okay, so then you can increase the value further and check what is the angle and what is the voltage across the individual element and give the fill the table option. Okay, so now what you do, you fix the inductor at one value and you change the capacitance value to all the three options and check what are the voltage, current and the phase angle. Then you give the fill the table option. Then you choose the inductance to the second value. Then again you change the capacitance from 0. Then here also you will be able to change it for three options. Then you fix it to the second value for the inductor and you change the value for the capacitance at 4 different steps and you find the all the values, that is voltage, current and the phase angle. Similarly, you fix the inductor at the final value and you change the capacitance with 4 different options and you fill the table. So like this, you take it for any 2 set of readings, means you fix inductance for 2 set of values and change the capacitance for four times and you find the relation between voltage and current, how the circuit is behaving, whether it is behaving like a capacitive or inductive. That you have to put it in the phasor diagram. Okay, your ultimate aim is to put the phasor diagram, but which how it is making it as a capacitive, how it is behaving like an inductive, that you should be able to explain. Is it clear? Is it clear? Do you have any doubt in this?
Yes, sir, clear.
Okay, so this is for this RLC experiment. Here you don't need to give any connections. You just take the data. You just keep the voltage as 220. By default, the resistance value 50 ohm and the LNC value you are going to change, and you are going to see whether the circuit is behaving like an inductive circuit or capacitive circuit. So you have to switch on this switch. If you keep the resistance value very less, then there will be some error. Okay, if I keep this as 4 ohm and if I try to turn on, you can see that click on the fuse. So here it has changed to red color one because this fuse is not capable of carrying more current. If you calculate 220 by 4, the current will be more than 50 ampere. But the circuit is designed for carrying only 5 ampere, so that it will be showing error. Okay, so now what you have to do for this step is you have to change the resistance value to, you keep it as a 50 ohm. After you keep it as the 50 ohm, you click that inductor value, fuse value. You can see here that now it has been changed to green symbol. Then you switch on this. If you switch on this, the circuit, it will be showing as closed, but here you have to see whether it is open or closed. It should be closed with this option. If you give the close option, then you will be getting the current flowing in the circuit. Okay, so this is for the RLC circuit analysis. Here you are going to plot the phasor diagram and you are going to analyze for the particular set of readings whether the circuit is behaving like an inductive circuit or a capacitive circuit. That is what you are going to do in RLC circuit analysis. Okay, so for today we will be seeing only 2 more experiments, that is open circuit test and load test of single phase transformer, and also short circuit test of single phase transformer. Okay, we will start with open circuit test and short circuit test of single phase transformer. So in open circuit test and short circuit of single phase transformer, whether sir has taught this in class? Can anyone tell me whether sir has taught this in class or not?
Hello, sir. Sir, transformers will be starting in the next class, sir.
Okay, fine. So can anyone tell me, some of you would have completed the experiments, right? Can anyone tell me why you are doing open circuit test and short circuit test of single phase transformer? Can anyone tell me why you are performing open circuit test and short circuit test of single phase transformer?
So to determine the efficiency voltage regulation of a transformer.
Okay, are you doing the same with load test?
Yes, sir.
Okay, what is the difference then? Why you need to experiment to do the same to get the same results? Am I audible?
Yes, sir, you are audible.
Yeah. My doubt is, when you are able to do, or when you are able to calculate the efficiency of the transformer using open circuit and short circuit test, what is the need for doing the load test? Already, some of you have completed the experiments, right? 3 or 4 groups would have completed already. At least, can you people answer to the question?
We didn't thought that, sir, actually.
Okay, whether the persons who are teaching that did not tell you that?
No, sir. The instructor told us to get help from the group who completed before us. So no.
Okay, fine. Okay. See, this open circuit test and short circuit test, the circuit connection are exactly the same like what we have done in the lab. Okay, the only difference is, actually, when you performed the open circuit test and short circuit test in a single phase transformer, your circuit would have been something like this. Okay, it would have been something like this. You would have connected an ammeter, then you would have got an wattmeter like this. then you would be having the transformer connections. Okay, you'll be having the transformer connections here. So this is what your actual circuit would have been if you have performed the experiment in the physical lab. So here you will be connecting the single phase AC supply. Okay, so now here in this wattmeter, this is M and this is L and this is C and this is V. This is the actual connection which we have given in the physical lab. Only difference between that circuit and this circuit is this. Okay, so actually here, instead of connecting this M and L, what they have done is they have connected the C and L connections, C and L terminals. Instead of M and C, instead of connecting M and C, they have connected C and L. Okay, actually, even if you connect like this or if you connect like this, it does not make any difference because this is a potential coil. Since it is a potential coil, whether you connect this before the current coil or after the current coil, it does not make a difference because the voltage drop across the current coil is very less. So you can connect this particular wire either to M and or either to L. But in this particular simulation software, simulation page, they have used connecting the C and L terminals. Okay, so all the connections I have given accordingly. There is no difference. Based on this circuit, I have given the connection. So based on this, I have given the connection. Only other changes. So here I have a secondary of the transformer. So the primary of the transformer is mentioned as P1, P2, and secondary of the transformer is S1, S2. So here I'm connecting a voltmeter. Okay, so when you connected in physical lab, suppose this is, let's say, this is voltmeter terminal 1 and this is voltmeter terminal 2. In physical lab, you can connect this voltmeter terminal 2 either to this point or this point or this point. Okay, then you can connect the other terminal to connect between these. That you can do like that. But in simulation, you cannot do like that. They have given certain instruction in this particular page itself. They have given instruction in this page itself. You just follow the instruction. You just give the circuit as per the instruction, and then you follow the instruction for operating it. Okay. So after you give the connection completely, after you follow the instruction, you give check connection. So after you give check connection, here we are using MCB. So instead of the voltage source there, we are going to use the MCB here. You are just going to click over that MCB. It is going to change from off to on condition. After you give from off to on condition, you just click over the auto transformer. If you just click over the auto transformer, that itself will settle to some voltage magnitude. Okay, you don't need to do anything. You just click over the auto transformer, then it will be settling at some voltage magnitude. That you will be getting it if you click the option as add to table. If you click add to table option, you can see that VOC is there and IOC is there and POC is there. This is the power loss for the core component. This is the current which is flowing in the open circuit, and this is the voltage across the primary terminals. Okay, so they have obtained 230 volt. Okay, so this is the way how you have to perform the open circuit. In open circuit, the circuit, this is what they have followed. This is what auto transformer they are having here. Here they are having MCB. Then here they are having an ammeter. So ammeter positive is here, ammeter negative is here, ammeter negative is here. Then you are having a wattmeter. Wattmeter M connection is here, wattmeter L connection is here. They have connected the C option. Let's say this is C and this is V. This V, this they have taken. This is the winding of the transformer. Okay, so this we will see. So this is the secondary of the transformer. In this, they have connected a voltmeter. So in this, they have positive and negative. Now, where to connect this point? Where to connect this point? There is a voltmeter. Where to connect this point? Okay. So now, this voltmeter, I'm drawing this directly. This voltmeter, they have taken and connected this to this point and taken and connected to this point separately. Then this this terminal, this V terminal. This V terminal they have connected to P2 of the transformer. Then P2 of the transformer is connected to this positive of the auto transformer end. Okay, this L is connected to P1. This is P2. This is S1 and this is S2. This is how they have connected it. But all these terminals, this is 1, this is terminal 2, and this is terminal 3. All these terminals are short circuited as per the actual circuit. But in this circuit, you have to give the connection in this manner, then only it will work. Okay, you just follow the instructions which is given there. I don't need to tell you anything. Just you can follow this instruction and you just follow the steps and simulate it. You will get the value of open circuit test. Then for doing the short circuit test, you click this option itself, which is below here. There is no separate link for short circuit test. First, you do the open circuit test. Once you complete the open circuit test, you have to click the short circuit test. Here the terminals S1 and S2 are open circuited. Now for short circuit test, you click it. Then one more link will be open. Here the connection is still same, except you are going to short the terminals S1 and S2. Okay. So here you have to connect this positive and negative like this. Then this should be connected like this. Then this should be connected to ammeter positive. Ammeter negative should be connected to M. So sometimes you may be correcting it wrongly. So it may be showing error. Only problem is it will not show where is the problem. So because of that, you may face a lot of issues. Since it is not showing where is the problem, it is difficult to find where is the error. Okay, so for this, we have to short circuit S1 and S2. You just give check connection. It is giving correct connection. So you just give add to table. Okay, I have to turn it on. So I have to click over the auto transformer. If I click over the auto transformer, then it is showing the display. It is displaying the results. Then I give the add to table option. Okay, so now it is showing the results of copper loss, short circuit current, and short circuit voltage across the short circuited terminals. Then if you give summit, it will be giving the value of this. Okay. So actually, what is this? Okay, I will be sharing you one video, why or how it is coming. Anyway, sir will be teaching you in class, but I will be sharing you one recorded video. You can just go through it, why it is coming like this. The complete transformer we are going to represent as a equivalent circuit like this. Okay, so actually what we are doing, if you are having a transformer like this is having primary winding and it is having a secondary winding. So now this complete thing we are going to replace it as a circuit like this. Okay, by open circuit test, what you are doing is you are finding the values of this is R, this is X. So you mention it as RCO, XCO. So this RCO is representing the losses which is happening in the core. Core means this is this material, this is the core material, which is of this rectangular shape, right? So that loss is represented by the RCO. So what is that losses? If there is some rate of change of flux happened in the winding, then because of that rate of change of flux, there is some fluxes which is available here, right? So rate of change of flux which is also happening on the core material. If the rate of change of flux is happening over the core material, then you know that since there is a circuit closing is there, then there is some EMF induced. Because of that some EMF induced, there is a current which is flowing through that. That current is nothing but eddy current. Okay, so this because of the rate of change of flux which is occurring over this winding, that flux is going to induce some EMF within the core in a smaller region. Then it is going to get a closed path because it is a conducting material. Because of that closed path and the EMF induced, there is some current which is going to flow in that particular core material. That current is called as eddy current. So this eddy current will be creating a loss, that is I square R loss. This is a current and there is some resistance for that particular path. So this is going to create a loss, that is I square R loss. This is like power dissipation. It will be happening as a heat dissipation. So the core loss will be reflecting in the heat dissipation. So that loss is going to be represented by RCO. Okay. Then XCO is going to represent the magnetic flux which is linking both the primary and secondary. Okay. This XCO is for representing the magnetic flux which is going to link the primary and secondary. So with open circuit test, what you are going to do is you are going to find this resistance value and you are going to find the reactance value. So this is for magnetic flux which is linking both primary and secondary. Okay, so this is with open circuit test. In short circuit test, what you are doing in open circuit test, let's say this is terminal A, this is terminal A, and this is terminal B. So you are open circuiting these terminals and you are finding the current which is flowing through this path. Because if you are open circuiting it, there is only one current which can flow through this path, is through this magnetic circuit. This is the core part. Okay, so now here the current flowing during the open circuit is very less when compared to the actual load current. The load current generally it may be rated for 13.6 ampere for the transformer which we have in our lab. So this magnetization current may be less than 3 ampere. So this current is flowing only to, it will be less than 3 ampere. So that current is flowing only to magnetize the core and it is going to accompany the losses which is available in the core. So this current will be very much lesser when compared to the load current. So it is considered that since this current flowing in the circuit is very much lesser than the load current, the losses which is happening in this path is neglected. If some current is flowing through the path, it is obvious that there is a resistor here and an inductor here, then obviously there will be a voltage drop will be occurring on this series element, but we are neglecting it because this current is very much lesser than the load current. Because of that, the losses which is happening in the series element, that we are neglecting it. The current which is flowing through the path, that we are considering only as the magnetization current. The magnetization current is helpful only to make the magnetization part. Okay, it is going to magnetize the core. That is what it is going to do, and it is also going to give the representation of the losses which is happening in the core. The core is nothing but the material which is mentioned in the square in shape. Okay, so that is for the open circuit test. In short circuit test, you are going to perform the short circuit test like this. So you are going to short circuit the terminals A and B. Now you are going to have a resistor here and you are going to have an inductor here. Okay. So now in short circuit test, what you are doing, you are going to find the current flowing through this path. So this current is around 13.6 ampere for 3 kVA transformer at 230 volt. Okay. So this resistance which we obtained in open circuit test, this value will be very much higher. These values will be very much higher. So because of that, the current flowing through this element will be very less. Why the current flowing through this element is very less? Because the other end, this is like a parallel path. This element and this element are in parallel, right? So this resistance are having very much huge resistance, and this inductance is also having a very much huge value. Because of that, most of the current will be flowing through this path. It will not flow through this parallel path. But one point to be noted here is, if in the open circuit test, if in the open circuit test, if you speak ideally, the current flowing in the open circuit test, the same amount of current should be flowing in this path also. So in the open circuit test, if the current flowing through this path is 3 ampere, now also the current flowing through this path should be 3 ampere, because the current flowing through this now also based on the voltage across this terminal. Okay. But here what we are doing, we are reducing the voltage, because if you are short circuiting it, this voltage source, this element and this element, it's almost like a parallel path. So this is having a very lesser resistance. This path is having a very much lesser resistance. If you connect 230 volt across this will be around 1 ohm or 2 ohm. So 230 ampere will be flowing through that, but the transformer is rated for 13.6 ampere only. Because of that, what you are doing, instead of giving 230 volt, now you are changing the voltage from 0 to some value. Okay, this voltage may be between 11 to 30, not more than that. You are going to give an input voltage that is going to be make the current, that is rated current, will be flowing here if you give within 11 to 30 volt itself. Even though the transformer is rated for 230 volt, it is sufficient for the secondary current to reach 13.6 ampere if you are providing the voltage as 11 to 13 volt, because this terminal is short circuited. This is of very much lesser resistance value, 1 ohm, and this will be of some value. Okay, so because of that, more current will be flowing here even you apply less voltage. So this current 3 ampere will be constant if you are applying 230 volt. If you are applying a 230 volt across this terminal, this 3 ampere will remain the constant irrespective of the load terminal or load current. Okay, what I'm saying is, suppose if your equivalent circuit is like this, if you apply 230 volt here, you have to connect the load here only. So initially, let's say that the load is taking 0 ampere. If the load is taking 0 ampere, at that time also there will be some current flowing through this path. Let's say this is 3 ampere. Okay, less than 3 ampere or some magnitude, let's consider it as a 3 ampere. Now I'm increasing the load, means from 1 ampere, then I'm changing to 2 ampere. Then like that I'm varying till 13.6 ampere. Now what I have done, I have changed the load in such a way that it consumes current, it takes current as 0 to 13 ampere. So the load current is varied from 13 to 0 to rated ampere. Even for this complete variation, the current flowing through the part will not change. This magnetization current magnitude will not change. Okay, why? Because the magnitude of the current which is flowing through this magnetization circuit is depending on this voltage. So since it is depending on the voltage, you are considering a fixed voltage. So because of that, even though the current varies of the load, the current flowing through the magnetization part remains constant, whether it is a 0 ampere or it is carrying the load rated current, that is of 13.6 ampere. So the point to be noted here is, from no load to full load condition, the magnetization current remains constant, more or less constant. Magnetization current remains constant. It will never change, provided you are fixing the input, you are keeping the input voltage as same. Because if you are changing the input voltage, the current flowing through this will be changing. If you are reducing the input voltage, then also the current flowing through that will be changing. So if you are keeping the voltage fixed, then irrespective of your current from no load to full load, the current magnetization current remains constant. Okay, so the point here is, if you are applying short circuit test, this is your overall circuit. Now earlier you applied 230 volt across this terminal for the open circuit test. At that time, now the current flowing through that is around less than 3 ampere. Let's say 3 ampere itself. Okay, 3 ampere itself. For 230 volt you got 3 ampere, but this is for open circuit test. For short circuit test, you are going to apply 11 to 30 kilovolt. How you will be fixing this voltage? You will be varying from 0 to some magnitude in such a way that you get the rated current at this terminal. So this is 13.6 ampere for the rated current for the transformer which is available in the lab. So you are changing the voltage magnitude of the source in such a way that you will be getting 13.6 ampere on the load terminal. I mean this short circuited terminal. Because of that, you are going to get very lesser voltage. If you get very lesser voltage, the current flowing through the path may be lesser when compared to the previous case. Okay, because the voltage applied here is less, the resistance of this is very high. So if the voltage is less and the resistance of that is very high, obviously the current flowing through that will be reduced. Right? Same thing is happening here. So in short circuit test, whatever the values you are finding, that is giving the parameters of this. That is series resistance and inductance value it is going to give. Okay, so this resistance and inductance is for the primary side. This resistance and inductance is for the secondary side. Okay, so what are these primary and secondary resistance and the inductance? Okay, so for that you can consider a transformer. This is a transformer. As I told before, this part, just a note. Whether my voice is clear? Is it more noisy?
It is clear, sir.
Okay, fine. So for
Yes, sir.
this part,
Yes, sir, clear.
yeah, fine, thank you. So here there are two parts. One is this core part. One is this core part. For that, by doing the open circuit test, we have found this component. For resistor and inductor, which is the series element, that is the resistance offered by this wire. That is the resistance offered by this wire. This is the primary winding and this is the secondary winding. Both side you are having certain winding. So that is having certain wire. That wire is having certain resistance. That resistance is offered as the resistor here because it is going to reflect in the copper loss. Means if some current is flowing through that, then current flowing through this will be I square R. Okay. So because of that, to mention this power loss, they have mentioned as a resistor here. Then for an inductor, it is going to reflect in reduction in voltage. This is going to reflect in reduction in voltage. How it is going to reflect in reduction in voltage is, if some current is flowing through this path, then this current, when it passes through the windings or turns, it is going to develop certain flux. So that flux, some flux will be connecting both primary and secondary. Some flux which will be established here and it will be coming through this. Means the flux which is established by this current, it will be linking only the primary coil and it is not linking the secondary coil. So that flux is called as leakage flux. If that flux is considered as a mutual flux, then more EMF would have been induced on the secondary side. Because of the leakage flux, some flux is not linking both the primary and secondary. Because of that, there is some reduction in voltage or EMF induced on the secondary side. Since it is considered as reduction in voltage, it is considered in series. If the same voltage is there, then it should be connected in parallel. Since there is a reduction in voltage because of the leakage flux, that is considered as a in series. Okay. So another part is here, this inductance is going to reflect the leakage flux, and since it is reducing the voltage, it is going to reflect in the series. That is another reason. And one more thing I wanted to say here is this always flux will be linked with the magnetic field. So when you are talking about magnetic field, you should be including the inductor. Okay. So when you're talking about flux, you should be representing as an inductor. That is what I have mentioned it here. Okay. So this resistor is going to represent the copper loss. This resistor is going to represent the leakage flux, which is available in the circuit. So for a primary, you are having a resistor and an inductor. For secondary, similarly, if some current flows, there is some power loss in the cable itself, and there is some leakage flux because of the current flowing through that. So that is considered as a R and L. So in the complete circuit, this is representing the series RL. This is on the primary side, leakage, copper loss and the leakage flux. This is for the secondary side. Secondary side, leakage flux and copper loss. Okay, so detailed explanation, I will be sharing you the recorded video. You can just go through it on what basis we have come like this, that I will be explaining. I have already explained to the other batch, that is EC1 group. I will be sharing that video that you can go through that. Okay, that is about that. So now, while doing open circuit and short circuit test, you are going to find these elements. The series elements, you are going to find it out in short circuit test, whereas this shunt element, you are going to find it in open circuit test. Okay, the aim of your open circuit test and short circuit test is to find the losses, and it is also helpful to find the parameters of the equivalent circuit. So two things we are finding: the copper loss, core loss, and the parameters of the equivalent circuit. So So with these parameters of the equivalent circuit, what we are going to do is we are going to find the efficiency of the transformer and the voltage regulation of the transformer. So efficiency of the transformer is given by output power divided by the input power. Output power means the power which is consumed by the load. Input power means the power supplied by the source. Okay, so you are going to connect the source here. Okay, so what you are going to do, you are having an equivalent circuit like this. Then now you are going to have the load here. You are going to have the RL parameters here. Okay, now what you did, instead of connecting this load, you did not connect this load in open circuit and short circuit test. Without connecting the load directly, you find the parameters of this element, this 4 elements, using short circuit test, and you found these 2 elements using open circuit test. All right, then what you found, you obtained the core loss and you obtained the copper loss. Core loss you obtained in open circuit test, copper loss you obtained in short circuit test. Now output power efficiency is given by output power by input power into 100. So this input power can be further divided into output power plus losses. This losses is consists of 2 parts. One is copper loss and the core loss. The core loss remains constant from no load to full load, whereas the copper loss is going to change as per the current flowing in the load, because the copper loss is given by I square R. This I is nothing but based on the load you are going to have this current. So because of this, the copper loss is going to be variable and the core loss is going to be a fixed loss. Okay, so this is a variable loss, this is a fixed loss or constant loss. Now you know the for some particular power. So suppose if you are connecting a load, now you know the voltage across that Vi cos theta. You are adding a resistive load, so you consider it as a 1. So you know for a rated transformer what is the voltage. 230 volt is the transformer voltage, and so for 100% of loading you are having, let's say, 10 ampere. For 10% of loading you are going to have 1 ampere. Now this output power is Vi cos theta. Again this cos theta is 1, you neglect it. This voltage is fixed, this voltage is fixed. Now this current is going to change, this current is going to change, and this copper loss current is going to change. Now what you are going to do, you are going to substitute the value of the current, and voltage is fixed. So for you can find the efficiency of the transformer without conducting the load or without having the load as it is. By open circuit test and short circuit test, you are finding the efficiency directly. Okay, now if we want to see that if the transformer is rated for 10 ampere, what is the efficiency of the transformer if it is carrying 1 ampere at the load end? So at that condition, you can substitute I is equal to 1 here, and I is equal to 1 here, and I is equal to 1 here in the copper loss equation. Then you can find the efficiency. Okay, so the point is, in open circuit test and short circuit test of transformer, you are going to obtain 2 things. One is parameters of the equivalent circuit, and the second one is the losses, core loss and copper loss. So with this, what you are going to do, you are going to obtain the efficiency of the transformer without performing the load test. Okay, so for any load condition, you can obtain the efficiency of the transformer without directly conducting the load test. Okay, so now what is the difference between this and the load test? In open circuit test and short circuit test, obviously you are finding the efficiency of the transformer and voltage regulation. Voltage regulation, sir will be explaining to you in the class. Okay, or I will be explaining this in the recorded video that you can go through that. Okay, so now open circuit test with short circuit test, you are finding the efficiency. Similarly, in the load test also, you are going to find the efficiency. So what is the difference between this and the load test? Why do we need to have 2 tests? See, here in this particular in this particular equation, we are fixing this voltage magnitude, that is as 230 volt, right? But in practical, this 230 volt, it's not going to be a constant value, because when you are changing the load, the input voltage may change in a different manner. Okay, the input voltage can be changing to 228 or 227. Those who have performed the experiment, they would have got to know this. The input voltage will also be changing to 227 or 228, even sometimes more than 10 voltage it may reduce. So since you have fixed the voltage value as a constant in the open circuit and short circuit test, here you are not able to find the exact efficiency. Exact efficiency you are not able to find it out. Whatever the efficiency you are finding, that is approximate efficiency. But in the load test of the transformer, there you can find the exact efficiency for different loading condition. Okay, that is the major difference between obtaining the efficiency of the transformer in open circuit test and short circuit test. Okay, just a minute. Okay, is that clear? Is that clear? Why do you
Yes.
need to find? Yeah, if you have any doubt, you can ask. Let me complete that load test of a single phase transformer. Then we can complete it. Complete this particular lab. I mean, we can end this particular lab. If you have any doubt, you can ask. Else, we can complete this lab after I show about the simulation. Okay, so this is the final experiment for this lab. So this is a load test on single phase transformer. In this link, obviously with this link also you can perform open circuit test and short circuit test, but there is some issues with that. So I'm not telling you to directly do the open circuit test and the short circuit test of the transformer with this link. Okay, but see, when you have to perform the load circuit test for this particular experiment, you have to do open circuit test and short circuit test also. Then only this circuit will work effectively. Okay, so now for this is the link where you have to perform the load test of the single phase transformer. So in that link, there are 3 tests. The first one is the open circuit test, second thing is the short circuit test, and third thing is the load test. So here you cannot use the load test directly. You have to perform open circuit test and short circuit test first. Then only you have to perform the load test. Now we have to perform the open circuit test first. So for open circuit test, you just give the input voltage as 230 and the frequency as 50 Hertz. Then you have to just switch it on and you have to simulate it in order to see the values. So here already 230 is given and 50 volt is given. What I'm doing, I'm just switching it on. It is giving some values, right? So after this, what I have to do, I have to give the option as simulate. There is an option here, you can see here that simulate, right? I have to give this option simulate. Then you can give the option as fill table. Okay, you again turn it on. Actually this you give the option as simulate. Okay, then you note down the values and you keep it for your reference. So here this is the power loss, this is the magnetization current. Okay, this is the magnetization current, this is the power loss, that is the core loss, and this is the voltage across the terminals, that is the primary terminal, that is around 230. Okay, so now this is for the open circuit test. Here the secondary of the transformer is open circuited and we have obtained the magnetization current and the power loss and the input voltage. Now what we are going to do, we are going to the short circuit test. In short circuit test, what we are going to do is we are going to short the load terminals and we are going to see at which voltage it is coming as 13.6 ampere. Here they have told that the approximate current is 13.6 ampere, that is the rated current. We want to change the voltage by varying this auto transformer value. You can see here that there is a part where I can change the voltage magnitude. Okay, this is the part where I can change the voltage magnitude. If I keep like this, then the voltage of this transformer, output of the voltage transformer is 0. Okay, so if I keep it as 1, if I keep it as 1 here, then the output of the voltage transformer is same as the input voltage. So initially I am considering it as a 0. Then after I keep it as a 0, I am switching it on. After I switch it on, what should I have to do is I have to gradually vary this voltage, but just by changing the slider. Okay, if I vary this slider, you can see that the voltage is increased. If I change this multiplication by your rated voltage will be the voltage across your transformer primary. You can see here that the voltage across the transformer primary is 21.85. So now actually the rated current on the secondary should be 13.6 ampere, but here it is coming as 18 ampere. So what should I have to do? I have to reduce it. So I am reducing it in such a way that I am getting 13.6 ampere. So here I can see here that I am getting 13.66 ampere. So what I did, there is an option to change the slider value. So I have just used it. So what I did, I changed the sliding option. So because of that, I brought the rated of the secondary current as 13.6 ampere. So if I get 13.6 ampere on the rated side, I have to stop changing the voltage. So after I stop changing the voltage, I should note down the current, voltage and the power. So this is the copper loss value and this is the current during the time and this is the voltage across the primary winding. So this is the short circuit voltage and this is the copper loss, power loss. Now after you did this, you have to give the option as simulate. So after you give simulate, you can see that there is some value which is given at the bottom, that is Re and Xe. What is this Re and Xe? These values are for the equivalent circuit values. Okay, so these are series element. For the equivalent circuit values, you are finding this Re and Xe. Then after you find it, what you have to do is you don't fill the table option. Instead, you just note down the values. Okay, you just note down the values. This is copper loss and this is voltage across the primary and this is the current in the HV side. Now what we did, we changed the voltage magnitude in such a way that we got secondary current as 13.6 ampere. That secondary current is the rated current. After that, what you have to do, you have to give the simulate option. After you give the simulate option, which is on the right top, you will be getting the values of Re and Xe. So Re and Xe value will be filled here. Now you go to the load test. Now you are having Rlc parameter, that is the load. Okay, that is the load. Here they have neglected the magnetization part. That shunt component they have removed it. Since it is an equivalent circuit, they have just removed it. They did not use it. So now what you have to do is, here in load test, you are going to use only the resistive load. So you just keep the inductance value and capacitance value as 0. If you keep inductance value and capacitive value as 0, then these two will be like this switch is on, that means short circuited. The inductance will not be included in the circuit and capacitance will not be included in the circuit. The current flowing here will be flowing through this switch and it will be coming here and it will be coming here and it will be flowing through this and it will be coming through this and it will be coming out of this path like this. Okay, so the current will be flowing through the switch across the inductor and the capacitor. The current will not be flowing through the inductor and capacitor directly. Now this complete circuit will become the resistive circuit because we are having only the resistive part. Now what we have to do, we have to choose the voltage and we have to choose the frequency. Now we have to choose the resistance value. When the resistance is high, you understand, when the resistance value is high, it means that the load is less. If the resistance value is less, then it means that the load is high, because when the resistance value is less, then more current will flow into the circuit. So you can say that the resistance is less means more current will flow, so it is loaded for more value. Okay, so now what I am doing, I am turning it on. Once I turning it on, it will give all the values. It is giving the input voltage, it is giving the current, and it is giving the voltage across the load. So now if I give the option of simulate, you can see here that it is giving the value of 90%. This is the efficiency of the transformer. That value is coming as 90%. Let us see, if I change the resistance value to 40, what is the effect of resistance? Means now the load resistance is reduced. If the load resistance is reduced, mean the current flowing through the circuit is increased. If the current flowing through the circuit is increased, then now we will see what is the efficiency of the transformer. Now you can see that when the current flowing in the circuit is more, the efficiency of the transformer is getting increased. Similarly, we will be changing till 17 ampere, sorry, 17 ohm. I'm fixing it as a 30 ohm. Then you see the efficiency of the transformer is 91.68. Now again I'm increasing to 20 ohm. Then let me see what is the efficiency of the transformer. The efficiency of the transformer is 91.722. Now I'm increasing the value to further. So I mean reducing the value to further. So I'm fixing 17 value, 17 ohm. Then I'm simulating it. I'm getting 91.45. Then so I'm keeping it as 16 ohm. The efficiency is reducing. Okay. So the rated current is 13.6 ampere. So I am till that I am varying it. So efficiency is still reducing, but you can see here that the rated current is coming. The current is coming as 13.25 in this ammeter. Now I'm increasing to 14 ampere. This 14 ohm. Now you can see that the current value is coming as 14.06. Okay. Now the efficiency is further reduced. Actually, what it is happening is, let me plot it. If I plot the graph, efficiency of the transformer will be increasing like this, then it will reach a certain peak. After that, you can see that this is around 95 to 98 percentage or 99 percentage of loading. You will get the peak at the time of 95 to 95 percentage of the loading. After that, the efficiency started decreasing. Means during the light load condition, the efficiency of the transformer will be very poor. During the higher rating of the transformer, when you are going near to the rated, the efficiency of the transformer will be keep on increasing. After you are crossing to 95 to 99 percentage of the rated power, 90 to 95 percentage of the rated power, the efficiency of the transformer will start decreasing. Okay, so we can forget about this, but let me explain only this point, why the efficiency is poor during that time. Okay, so let me draw the equivalent circuit for that. If I draw the equivalent circuit for the transformer, the circuit will be given like this. Okay, the circuit will be given like this. Now let's say that my load current is zero. Load current is zero. Okay, so now if I apply 230 volt across this, then some current will be flowing here, that is going to do the magnetization part. Now the load current is zero. If the load current is zero, if you obtain the efficiency, now what is efficiency? It is output power by input power. Your output power is having some value because some current is flowing through that path. Because of that, there is some voltage and there is some current. Obviously, you can obtain the power. So you are having certain input power. Since the load current is zero, the output power is zero because output power is given by IL square R, right? You are connecting a resistive load. Because of that, the current flowing through that is zero now. So because of that, the efficiency of the transformer is less. Now, when you are gradually increasing the load current, what happens is this current will be keep on. Let's say this is 1 ampere and this is 3 ampere. Okay, this magnetization current is 3 ampere and the load current is 1 ampere. Now you will be having one input power and one output power. Okay, so now this is having copper loss plus core loss plus the output power, right? So this is there, only output power is going to vary. So when the output power is going to vary from 0 to some maximum value, what is going to happen? This efficiency is going to increase, because at light load condition, what happens is the current flowing through this path, light load condition means the current flowing through the load will be lesser than the current flowing through the magnetization current, or the load resistance is the load current is almost very negligible. So when the load current is lesser than magnetization current, that time your input power will be very much higher and output power will be very much lesser. Because of that, your efficiency is very much less. when you are loading the component, what happens is there will be some condition where your IL will become greater than IM. That time, after that, your efficiency will be keep on increasing. Okay, so when it is at the light load or no load condition, the efficiency of the transformer is very poor. When the transformer is operating at 95 to 100% of the rated load, it will be having the maximum efficiency. Okay, so after some 95 to 99, the efficiency will again going to dip. That is not required for you, but you just understand that during the light load condition, you are going to have the less efficiency. After this, what happens is the copper loss is going to increase further. So because of the increase in copper loss, the efficiency is going to decrease. Okay, so here the core loss is there always, and copper loss before this region, the core loss was there, and copper loss was increasing as per your load current. Okay, after some instant, what is happening is the copper loss is going beyond some value. Because of that, the efficiency of the transformer starts dipping because your load current is increasing. If your load current is increasing, then the loss which is happening in the series path is also increasing. There is some extent. After that, some extent, the copper loss is going to be very much higher. Because of that, the efficiency of the transformer is going to dip after some time. Okay, so for this experiment, what we are doing is we are including the load with, after including the load at certain particular point of loading, we are going to say in terms of rated current. So 13.6 ampere is the rated current, then 1.36 is the 10% of loading, and this multiplied by 2 will be giving the 20% of rated loading, and if I multiply this till 10, this will be 30%. Like that, to obtain the rated current, I have to multiply this with 10. Then if this is the 10% of the loading current, then the overall loading current will be 13.6 ampere. This is the rated current. Okay, so now what I am doing, I am changing the load at different percentage of the maximum loading. So accordingly, I am obtaining the efficiency of the transformer. After I am obtaining the efficiency of the transformer, I am going to plot it, and I am going to see where the efficiency is higher and where the efficiency is lesser. Okay, so the efficiency of the transformer, you will be having the maximum value when the fixed loss is equal to the variable loss. Okay, that also you may be reading in theory. So you will be getting the maximum efficiency when the fixed loss is equal to the variable loss. Fixed loss is the core loss, and variable loss is the copper loss, because the copper loss depends on the load current. So this is based on I square R. So this I is going to change as per the load. So this is considered as a variable loss. So you will be getting the maximum efficiency when the fixed loss is equal to the variable loss. Okay, so this is about these experiments. If you want me to explain about this, so for this particular link, you have to perform the open circuit test and short circuit test. Then only you can perform load test, because in this load test we need RE value and XE value. RE value and XE value can be obtained only if you have performed the short circuit test. So if you perform the short circuit test, after you perform the short circuit test, you give the simulate option, then you will be getting the RE and XE value. That value will be fixed to this load test for this series connection. Then you can obtain the load test of the single phase transformer. So here you are going to change the load resistance by from the rated value of 50 to the minimum value of 14. Okay, the initial value should be 50 ohm, and the final value can be of 14 or 13. Okay, for that itself you can see that we got 14.06 ampere. For 14 ohm, if I fix it here, if I keep 13 ohm, then there may be a possibility this fuse may get blown off. Okay, so because of that, you should not go for lesser resistance than this, but for higher resistance, you can perform the experiment without blowing the fuse. Okay, so this is the thing which I wanted to discuss today. If you want to ask anything, you can ask, else we can end the meeting. Thank you for your patience. I hope that you understood something out of this lab. Okay, I will be sharing you some recorded videos which you can go through, which I had already taken for the EC1 batch. Okay, actually a lot of your labs got cancelled, but I have taken all their labs. So because of that, I were able to explain them the theory also. Okay, so that's all from my side. If you want to ask anything, you can ask, else we can end this meeting.